So, hi everyone, I am Anuj Kumar, and this is the assignment 4 for this NPTEL course Colloids and Surfaces. Okay, so the problem 1 is uh, very descriptive. So, in this particular problem, you are given some basic theoretical views, and after that, this problem is designed. Okay, so what is given here, the concept of negative Hamaker constant can be used to explain particle engulfment by an advancing solidification front. Okay, so this is accomplished by the considering a dispersion of solid particles, and the liquid medium is allowed to solidify by subjecting the dispersion to a thermal gradient. Okay, so the negative Hamaker constant, if the value of Hamaker constant is negative, then it will show the particle engulfment. Okay, and so based on this logic, a laboratory experiment was performed by considering liquid naphthalene, which is dispersed with different dispersed particle. Okay, dispersion medium, that is polystyrene, nylon 6 Teflon, and nylon 12. So the liquid naphthalene is solidified, and it is required to find if the dispersed particles are engulfed or rejected by the solidification. So you have to just find out where the in for particular dispersed phase the particles will be engulfed or rejected by the solidification front. So here are the surface tension of solid naphthalene and liquid naphthalene are given, which is denoted by 1 and denoted by 3. So gamma 1 is equal to 26.4 millijoule per meter square, and gamma 3 equal to 32.8 millijoule per meter square. Okay, so you have to consider some table and fill up the entries. Okay, based on the engulfment or rejection you will get. Okay, so this is particular hint given here for the Hamaker constant term. So you have to just expand it and put the values, and you will get the value of resultant Hamaker constant. And based on that value, whether it is positive or negative, you have to just write the engulfment or rejection. Okay, so these are the interfacial tension we given for different dispersed phase. Okay, so you can consider it gamma 2. Okay, so if I just expand this term, that is gamma 3 2 1. Okay, so you will get, sorry, this will be a from theoretical, you will get something like this. Okay, sorry. So let me just write these values here. Gamma 1 26.4, it is 32.8, gamma 3, and gamma 2 you have to select on the basis of the dispersed phase you are using. For just like example, I am taking for polystyrene. Okay, so for polystyrene, gamma 2 value will be 27.6. Okay, so you have to just put this value here. This is constant, and gamma 3 value is 32.8 power half minus 27.6 half, and similarly gamma 1 is 26.4 half minus 27.6 half. So some mathematical calculations, you will get this term positive and you will get this term negative. So resultant will be the negative Hamaker constant. Based on this, it will show the engulfment at the solidification front. Okay, and similarly for other dispersed phase you can calculate. Okay, so let me write here E. Based on E or R you will get just mention here. Okay. The next question is, consider a dilute dispersion of cube-like particles. Assume that each side of the cube is 1 micrometer or 1000 nanometer. A small quantity of non-adsorbing polymer of radius of gyration is given here, 2 Rg, that is 10 nanometer, and the concentration of polymer is given, or you can say is it the number density, 20 molecules per meter cube. Temperature is given, and if the interaction potential cubes can be modeled analogous to interaction between two flat plates. I will discuss about it later on. So calculate the strength of interaction when the distance of separation. So here are the different separation distances given. On based on that, you have to calculate the strength of interaction. Okay, this is the Boltzmann constant value given here in the thermal energy. You have to calculate the answer in terms of the thermal energy. Okay, and that means if you are getting something x, so it should be x kbt, not x, it's going to be y kbt. Okay, so but it should be in terms of thermal energy. Okay, so 2 Rg, you can write here the sigma. Okay, so this is the situation. Okay, that is the question describes. This is like this. So this is the depletion volume. Okay, and this the polymer and just half the radius of gyration. Okay, you can more find out about this problem on this particular link. Okay, let me just calculate. So the formula is minus n kbt sigma minus h, if sigma greater than h. Okay, and it will be 0 if sorry, just I'm writing here p overlap or delta v. Okay, if sigma greater than h, then this condition will be there, or if sigma is less than h, it will be 0. So in the first case, you can see here the sigma value is 10 nanometer. Okay, and the h is 20 nanometer. So second case will be applied here, so the interaction potential will be 0 for this case. Okay, if I calculate for this, you have to just follow the simple calculations. I can just expand it, the v overlap. So v overlap is equal to, can be sigma minus h into area, and sigma, if you sigma is given here the 10 nanometer, and the h is 9.9. So you can calculate the sigma minus h and multiply by area, you will get the overlap volume. Okay, and n is the number density that is given in the question, that is 6.910 to 20. So you can easily calculate the minus 6.910 raised to 20. You can write kbt as it is, because you have to get the answer in kbt terms, and the v overlap value put here, you will get the answer in range of 20.5 minus 19.5. Okay, this is the third problem, that is basically based on the theoretical aspects. So the addition of polymer to a colloidal dispersion, yes, it increases the viscosity of the colloidal dispersion. Okay, and it can also stabilize or destabilize the colloidal dispersion. In about these concepts, I will discuss in details later on. So at this time, you have to just select the correct option. So this will be the correct option also. This is also the correct option. This is also. So this option will be the right answer for this. And the following is type of a attractive interaction that arises because addition of polymers. So you know In one particular case, if this is the colloidal particles and the polymer is absorbing in its surface, like brush like structure are formed, but they repel each other. Okay, that is the repulsion, not attraction. Van der Waal interaction do not arise because of addition of the polymer. Without polymers, it exists. Okay, so this will be the wrong option. This is also the wrong option. This is also, so none of the above will be the right option for this. The problem 5 is the destabilization of a colloidal polymer mixture can occur due to first option is the breaching, second is the depletion interaction, and third is the steric stabilization and steric repulsion. Okay, so the destabilization. If I talk about breaching, okay, so if this is one particle and this is the polymer, so it can form a bridge. So the particles may be aggregate because of the application of this polymer. So this is also example of destabilization. Depletion interaction is also an example of the destabilization because let's say if this is the container and these are two particles. Okay, so depletion means that is the very less distance between here. Due to the osmotic pressure gradient, the particles come close to each other. That is here pi is equal to 0 and here is some value of pi. So the osmotic pressure gradient arises and that's why the particle come close to each other. So that is also example of destabilization. So this is not a destabilization. This is also not a destabilization. These two are the stabilization of colloidal polymer mixture examples. So this option will be the right option for this. And similarly, C and D, the correct option for the stabilization of colloids. So let me discuss one by one the different phenomena. So if you have a low concentration of polymer, so there the bridging flocculations may occur. Okay, so what happens there? The polymer chain forms bridges by absorbing one more on more than one particles. Okay, so the polymer chain works as a bridge between two particles here. If you have a at higher polymer concentration or medium polymer concentration, the steric stabilization will be there because this brush-like structure can extend over sufficiently long distance and they mask out the influence of the van der Waal interaction between these two particles. So that is known as a steric stabilization. So for steric polymerization, stabilization, sorry, the polymer molecules must be either adsorbed or anchored on the particle surface. Okay, and the third is the depletion flocculation. You can see here there is very less distance between the particles. Okay, so here only the influence of polymers are seen. Okay, because the polymer chains are free in this case. Okay, so when the particles are close to each other, that is the surface to surface distance is very less. Okay, so the exclusion of polymer chains in the region between two particles causes depletion flocculation. Okay, so I have already indicated the depletion effect is an osmotic effect and occurs when non adsorbing polymers are added. Okay, so this is the next problem, that is a van der Waal interaction between two spherical particles of identical radius separated by surface. So you have to just uh, derive the expression if two spheres are having the identical radius for the van der Waal interaction. Okay, so if I denote the van der Waal interaction, this is the formula, that is R1 R2 R1 plus R2. Okay, so simply just put R1 equal to R2 equal to R. Okay, and this will be R square, this will be 2R. Okay, so you will get the minus AR upon 12D. Okay, so this will be the right option for this. And similarly you have to express the force of the system. So if you uh, just do this simple derivative, you will get, what will you get, is minus d by dt ar by lb. So this will be positive, constant will be outside, this will look something like this. Okay, and ar by 12, it will be minus this, that is minus ar divided by 12 d square. So this will be the expression for force. Okay, so this was all about this session. This was a very important session. Some theory based questions were there, and there were some, there were two numerical problems. Just try to solve for these disperse phase by yourself, and this is also a very technical question. So uh, here just what is different here, here are given the cube like particles. In most of the cases you will deal with the spherical particles. Okay, so this is all about this session. uh, Thank you very